Now you know that I have the equation for thermal noise. If I have the voltage root mean square value, I can find the current. So if I know the voltage, see En square, it is going to be the thermal RMS value. So voltage square value is given. So from this I can find what is the current square value. By Ohm's law, I can find current square equal to voltage square by R square. Voltage square value is 4 kTr del F divided by R square. So 4 kT del F by R, you know 1 by R is given by conductance, capital G. So 4 kT G delta F. 1 by R becomes G. So either you can represent the thermal noise in terms of a Thevenin's equivalent circuit having a voltage source series with a resistance, or you can represent thermal noise using a Norton's equivalent circuit. You are going to have a current source parallel to the resistance. And direction of current source, it is not of importance to us because noise itself is not of very much importance to us because we only find the magnitude of noise. We are not bothered about the direction. So the current direction, some books they give it for flowing down, some books they give it flowing up. That does not matter as long as we are able to find the magnitude of whatever noise we are concerned about. Okay, so that is what is given here. The first diagram, what you have seen is the Thevenin's equivalent, where you have voltage source series with a resistance. The second diagram, you call it as Norton's equivalent, where you have current source parallel to resistance. And remember, the equation, whatever you have studied, En square, it is voltage square. Okay, it is voltage square. It is not voltage. If you want to find voltage, you have to take square root for this. So that is why I'm finding current square here. RMS value of current, thermal noise, In square equal to voltage square by resistance square. This is coming from Ohm's law. The Ohm's law is valid only for constant temperature. Assuming that this T is constant, we do all these calculations here. Otherwise, you cannot even use these equations for drawing the equivalent circuit for thermal noise. Okay, so these are some of the mathematical models available to quantify your thermal noise. Again, in all these expressions, the Cn bar, In bar are not instantaneous values. They are the root mean square value of voltage and current which are observed for a long period of time. As I said, noise will not have a single value. It is going to vary instantaneously, right? So these values En bar and In bar represent the noise, voltage and current which are root mean square values which are measured over a period of time, and that value only we are going to substitute in the equations. As I told you, the polarity of the voltage source, the current direction are not important here. So that is not important in the sense we are going to take only the magnitude of the noise. So that is going to be immaterial. And the very important thing, the noise will have a zero mean. So if you add all the value of noise which is available to you and divide by the total number of samples you have taken, you will get the answer to be zero. So which means the noise has a zero mean. So all the samples, if you add and divide by n, you might have a zero mean. See, when you compute mean, you should not take magnitude, you should take positive as well as negative. So in that way, the positives and negatives will get cancelled and you will get a zero mean. But if you are finding RMS, you are squaring the signal. So even negative will become positive. So RMS will never be zero. The root mean square value will never be zero, but the mean value of noise is going to be always zero. So it is going to be always zero. So how I can minimize thermal noise in a given system which is going to use resistors? So only way to minimize your thermal noise is you have to ensure that the temperature has to be as low as possible. Low temperature operation is perfect to keep this noise under control, or whatever resistance you're going to use smaller value of resistance, or use a system which is going to have a minimal bandwidth. So these are some of the most effective techniques which will ensure that my thermal noise is not going to disturb my system. Otherwise, these thermal noise will have a cascading effect on the performance of your system.